session so you can talk to the AWS engineers directly. So here is a very short video we've made for this promotion, for promotion of the event. Just have a look, check it out. So this is the AWS Summit happening this April and May the 1st. I'm not sure how many of you guys have been to this summit. It's a very amazing experience. And then we bring the AWS Summit to the USYD.
Welcome to the Immersion Day to know more about cloud computing. Come to join us, and I will see you there.
Okay, so if you are interested in AWS Immersion Day, join us now on October the 18th from 11 a.m. to 2 p.m. And here, yeah, all right. So here is the QR code for event registration. So if you want to learn more about our society, you can search Facebook, WeChat, and LinkedIn to type in Cloud Society, and you can see the event details and everything we've posted for this event and future events. Thank you, guys.
Okay, everyone. So we continue with with our normal lecture. So today we are going to cover another type of NoSQL system called key value storage systems. So that's the outline. Right? We'll give like a very, very brief overview because this is like the simplest system you can have. So it does have a lot of different ways to implement it. And we'll have a brief intro to the very simple way of implementing it, which doesn't involve a lot of persistence. And then we'll move on to the main topic today, which is Amazon's Dynamo. Again, we'll give an overview, and we're focusing on, it does have a lot of technologies. So we're focusing on the partitioning technology and also the replication and consistencies. So we don't go through everything, but we're only focusing on these two very important technologies. Okay. So key value data model, as the name suggests, is a very, very simple form. It's like simplest form of data model you can think of. So basically, each data record consists only two pieces of information. One is a key, the other is like a value. And then all queries, they are like value-based, also key-based. So you have to, you query a key and then you find a value, or a range of key to find the values. So there are similar concepts in programming language or data structure, like associative array, depending on which language you're using. So the term could be different, but they refer to very similar things. Associative array, hash map, hash table, or dictionary. So they all refer to this simple key value, like a data structure. And like there's a basic API, again, very basic. We don't have a lot more, like additional ones, only basic ones, like put and get. So put is, and it's very similar to those ones in the hash table. So put is like we put a key, we put a value to associate key, and we can retrieve the value by giving a key. So we have a put and get. That's two basic APIs. Usually it doesn't have, that's the basic ones. You might get a few very limited additional ones, like probably like scan a small range. So there are many such systems because it's so simple. So there are many different ways to implement it, and for very different purpose. And because they're for different purpose, so they basically optimize like different aspects. So some might just provide very pure key value form. Well, the system might just treat the value as, system will not try to understand what the value is. It treats this as like uninterpretable, either string or byte array. So it will just, once it will try to put the value in and then retrieve it out and then give it back to the client. It will not try to understand what is in it or try to decide if it is a valid or not valid. Others may add some further dimensions in the value part. Like the value can be a JSON document, and then there's a key point to the value. So it's like in hypertext. Or the value can contain like columns and corresponding values. So it's like the value itself is like a row. This is like big table or HBase. So big table sometimes is considered, also has this key value flavor. Okay, so in the key value store or key value data structure, so the key can be of any type usually. And like string, number, date, and time, or very complex object. And most often, we don't really use the raw value of the key because it's pretty unpredictable and has a lot of like unique values. So most likely they are hashed to get like a value of fixed sizes. And we also have like, we know what's the maximum value of it. So hash function is a very useful and very flexible one. Usually they can be used to map data of any type or arbitrary size to a fixed size. So that's very useful property. So it doesn't really matter what the raw data looks like. We can always have some hash functions and then convert it into data of fixed size. Like we can have like a Wikipedia page. Some are pretty big, some are pretty small. But each Wikipedia page can have a unique hash value using this SHA-1 algorithm. And then we can produce something called a message digest. And this is of like 160 bit value. And so even like a small change to the content will generate different values. And then so we can use that it's an easy way to compare if the two versions are different. So the result is usually called a hash value, hash code, hash sum, or hash. And there are many different hash functions depending on what sort of like value you want to get. So it allows for very efficient storage and lookup, because if each unique one corresponds to a single value, And then you can use that to do. So the lookup basically involves just like looking for that particular. So you don't have to go through like a long list and keep doing comparisons. So it's something like that. If we have key like this, and that's the hash, so we can design like a hash table, while each hash entry is corresponding to the actual values. So 1 goes to the first row, and 3 goes to here. Currently, we don't have anything hashed to 2, so this row is currently empty, and then that's 4. So looking for information is pretty easy. If we want to find information about Alice, we find its hash value, and then we know it's here. It's like we already know the location, and then we can get the data. So that's the basic principle for this type of systems. So there are many such systems. So some systems like deals with only in-memory, like in-memory storage. It doesn't worry about like persistence because it's specially designed for caching. So the real data is basically, or it's stored somewhere. It's just sometimes we need to use the data, and we need to use the data multiple times, and we don't really want to keep going to the persistent storage to get it. So we want to hash it in the memory for efficient retrieval. So that's some motivation for a type of system called man-cached. It's a very early in-memory key-value store system. It's very, very early. It's earlier than the terminology NoSQL storage system actually coined. But nonetheless, it's considered as a type of key-value storage system, and a relatively simple type to give you some idea of the technologies we might use in other more complicated systems. Yeah, so the motivation, as I said, it's to provide caching for web application. Mostly like it can provide the cache for at the database layer or at the web server layer. So the idea is to reduce the actual the I/O and reducing the network, and we can get cache. We can get data from cache straight away. Okay, so the simple solution is like to have a global hash table that all web process on all machines could access simultaneously and instantly seeing one another's change. So it's like we want to have some global things, so we can cache the session data. We can cache other data like we retrieved recently from the database that might need to be used in the following up request. Okay, so it's a in-memory system because it's only a cache. So durability is usually not part of the consideration. And so because the data, whatever it's caching, is already in the database, so that's provide the durability. And this system is mainly for boosting the performance, like reducing the latencies. And so no replication is implemented, so making it very simple. Usually when there is replication, remember, there's a lot of things you need to consider, but if there's no replication, the system can become relatively pretty simple. And there's mechanism for guarantee like freshness, because that's the top requirement for like being like a cache. So they use different things like expiration and validation mechanism. And cache miss is pretty common, but it's okay. Like if it's missed, so you just go to the original place to get the data. And what they provide is like a distributed cache store, which means they want to utilize free memories on all machines. And basically, so there are a lot of machines, and some like a web servers, some are others, but there's like all the machines probably doing something, and there are some free memories. And each machine may run one or more mem-cached server instances. So it's like running a process, managing the available memories. So you basically, like the machine will allocate some memories, like that's being used by mem-cached, and there's a process running there responsible for managing it. So why like one or many? Because sometimes you can install many physical memories in a single machine, and you can install up like more memory than the actual address space supported by OS. So OS currently like there's 64-bit. That's the address space. So you might install like more physical memories, and then in that case you probably need to run multiple memcached instance. Each has its own like address. Okay, so let's see how they try to build this like this global hash table, and making it like accessible from all the, like web servers or client. So the key of so there's a global hash and there's a keys. So again, just as any hash table, there are a lot of keys, and the keys is not really stored on a single machine. It's distributed among a number of memcached server instances. And then, how do we know, like, okay, which key is stored in which server? So we need some simple rules to help us to decide. Okay, so, and we don't want this to be very complicated, because in that case, we might spend lots of time to figure out where is the key, or to maintain like the location. So the simple solution is, again, we make sure like each memcached instance, or it's like a process, is totally independent. It doesn't really know how many others there are. So they only manage their own things. And a given key is always kept in the same server, so it doesn't really keep migrating. So like once it's decided, okay, this key belongs to this server, and then it always goes there. And so you always go to the same server for the key. And there's a client library. Of course, we need to have something that kind of have global knowledge, because each instance doesn't really know the other ones, but there is another thing that knows it. That's the client library. It knows the list of servers, so all the servers, 5, 10, or whatever, and can use basically use predetermined partitioning algorithm to work out like a designated server of a key. So the algorithm can be complicated or can be simple. But here we just see a very, very simple ones, using like simple hash partition. This is as simple as it can get, and there could be more complicated ones, but that's it's not of interest to this course. And anyway, we're going to see like a more complicated hashing or partition way in Dynamo. So we just see the basic hash partition way. So what we do is we treat each memcached instance as like a bucket. And so instance with larger memories may represent like more buckets. So it's like one instance may have one bucket, and others may have 2 buckets. And then we use a modulo function to determine the location of each key. So basically, that's the very simple one. We just mode the number of buckets. And then each bucket has a unique ID from, if there are like 3 buckets, and then the ID would be from 0 to 2. And when we do the mode, we always get a number. If we mode like 3s, we always get a number like 0, 1, or 2, and that's indicate the locations. And this is actually used in lots of systems. Like if you done cloud computing, you know that's how keys are allocated as well. So again, we take a hash of the key, and because the key, original key is not really like a number, and it can't be moded, so we take a hash of the key and then turn it into a number, and then we do the mode. So the mode is also just like a very simple hash function. So it's like we use like 2 hash functions. One is hashing the key to a value, and then do a mode, and then to locate the bucket. Okay, so let's see example here. So this is a web node which runs the client library, which knows, okay, there are like 2 mem-cached servers, and we know the unique ID of the servers. And the one server doesn't have a lot of free memory, so then we consider this as containing only a single bucket and with number like 0, ID 0. And this one has, the other server has a little bit more memories to be used by memcached. It's like 1 gig. And then we consider this one has, this server has like 2 buckets, and it has the ID 1 and 2. And this client actually knows, okay, the bucket with 0 is here, and bucket with 1 and 2 is here. And each time, if we need to find something, first we hash the value. There could be other web nodes. They all run this client. So the client needs to be configured initially to know that these are the memcached servers. And if there's any change, the client needs to be updated. Client library needs to be updated. So it doesn't need to save any mapping, because the location is determined pretty easily just by running a mode. So each time if the client receives something we want to load the data belonging to foo and bar and bars, if we give 3 keys, and the client will work out the hash value of those keys, and then if this is 17, 16, 30, and then take a mode, and then this one, okay, it says, okay, this mode is 2, so it says this is in bucket 2, and this is in bucket 1, and this is in bucket 0. So the client will contact the memcached server, corresponding memcached server, to get the value of the keys that is required. So that's the very simple way of deciding where the data is. And then inside each memcached server, it has its own way to decide, okay, where is this key's data is stored. Okay, so that's a very simple overview and introduction to some simple system, simple implementation. So this doesn't involve replication or like fault tolerance, recovery from like crash. So all of this is kind of maybe covered in Dynamo. Okay, so Dynamo is a system is designed and implemented inside Amazon. Again, it decided not to use any of the existing systems, but to implement their own system. It's because they have some special requirement for their data store. So one particular thing they identify is like majority of their services in Amazon only needed primary key access to data store, like shopping cart and a few other things. So they don't need very complicated like SQL type of queries, because their query requirement is very, very simple. But at the same time, they do have requirement for other things, and they really want to optimize those. So they want to basically sacrifice like the complexity of query. They want to support very simple queries. To sacrifice that query complexity to support other more important features, which is like scalability and availability. That's a very essential, like in terms of their service level agreement. And in particular, they have this, they set up their own goal is like they want their system to be always writable, which means the write should never fail. It doesn't really matter how bad, well, like how many servers are currently unavailable. So as long as like some server, like in their whole server farm, as long as like some server is still available, they want any write to be able to be successful, like to be able to return successful to the client. So in particular, like when give an example of the shopping cart is like each time when the user is updating a shopping cart, like adding or removing things in the shopping cart, they always want that to be successful. They don't want the user to get some response saying, yeah, you can't really add something to the shopping cart or remove something from shopping cart. So they want to give the user the guarantee that whatever they want to do, like update, it's always received by Amazon and put somewhere. And they also want to have guaranteed latency and also like highly available. That's kind of similar to this always read, but this is more related to maybe with read as well. So write is always right. It's always writable. That implicitly suggests it's highly available, right? They also want the read to be available as well. So the design consideration is because it only needs primary key access, so there's no a point to separate between like what is the different part of the values. So they keep like a very simple key value store. So as long as we know this is the key and that this blob is a value, that's fine. And they want to sacrifice strong consistency for availability because certain database rule suggests you can't get everything. If you want both scalability, availability, and network partition to sustain network partitions, you have to give up something. So they give up strong consistencies for availabilities. And they try to resolve the confliction, like if there's different versions of the data, they resolve this during read instead of write, because again, they kind of treat write as like has higher priority than read. And they have this incremental scalability, which means basically they can add or remove servers to like running clusters without really impacting the performance of the live queries. Oh, this is just example of their service level agreement. So most of the application. So again, they're like a web from a normal client view. They are like a web application, right? And then you visit from a browser, and then you type in something, and you expect to get, like you search something, maybe a book, a toy, and then you expect to get the result as another web page. Well, it looks like as if it's just like a regular web application, but it does have a lot of services behind that to support constructing the result of like this or that queries. So there's a lot of services. And any simple query actually requires a lot of services, and they try to, so that's necessarily mean there could be a lot of latency. Latency can happen at any services or any aggregation layer, but they still try to provide like pretty good latencies in their service level agreement. So majority of the data in Amazon is stored in Dynamo instance. So that's the very end. And then going from the very end to the client, it needs to go through a lot of passes. And they try to make sure this is very, very efficient. So to minimize the latencies. And we're focusing on here. Of course, they do have a lot of other things on the other layers, but that's not the main thing here. We're only focusing on the lower level where the data is. Okay, Dynamo is, so Dynamo has quite a few key techniques, and as I said, we can't really go through all of them, even though it's only a single paper, but it's a very densely packed paper. It has a lot of things there. It doesn't give you enough examples to understand, so we'll try to supply enough example to help you understand different techniques. So first thing that making Dynamo quite different to all the systems we have seen so far is this is a purely decentralized peer-to-peer system. So they kind of mean the same thing. We just emphasize it's a peer-to-peer system. It's decentralized. So this means there's there's not a single node or group of nodes taking the master role. So every node in the system is like doing the same thing. So all nodes basically taking the same role. So that's very different to what we've seen so far. So in most of the systems we've seen so far, there's something like a master, or at least something that has overall knowledge of the whole system and is responsible for managing like the metadata or other things. But Amazon is designed, so like nearly all of Amazon's systems are designed following this architecture, like peer-to-peer ones. So it's like it's an initial choice they made, and eventually they follow that. It's just like Google. Initially, they choose this single master and multi-slave system, and then all this, and they build a lot of experience along the way. So they basically stick to that architecture. And Amazon is the same. It's just choose a very different one, and they stick to that because. So it's hard to say which one is better because you need to follow very different design principles, and you can eventually achieve a very similar result. So anyway, so Amazon initially decided, because they started as like a very distributed, so their CTO is like has strong distributed system background, so that's probably influenced the initial choice of their systems, like purely decentralized peer-to-peer systems. Okay, that's the few techniques, and so the problem is solved, and the technique used, and advantage. So first, partitioning. Like when we have a whole range of servers that can hold our data, and we always need to decide where to put our data, right? And we've actually seen quite a few different ways how to partition the data. So again, Amazon used something that's quite different that you haven't seen so far. It's called a consistent hashing. And that's something we're going to spend quite a few time on. So this advantage is support incremental scalability. And like you can add or remove nodes without really impacting the whole system. It will impact some, but only like it's like a localized change. And it wants to have very high availability for writes. And then this means sometimes we might need to keep multiple copies because the write might happen at different places if certain server is not available. So the direct impact of this is there will be multiple copies exist in the system. And then you need to come up with a way to decide, okay, which copy is the latest one. And then they use something called the vector clock. So this is used to reconciliation, like different versions. And so the advantage is like the version size is decoupled from update rates, and we will see why. And how do they try to handle temporary failures? And again, always achieve this high availability and always writable. They use something called slow pqrn and hinted handoff. So that's a way to make sure that even if all the nodes maybe like supposed to handle this data is not available, we can still have a way to write it. They use something called slow pqrn. Again, that's we're going to cover. And how to recovering from permanent feature, use something called anti-entropy using Merkle trees. So that's we're not going to cover. And the membership and failure detection, use gossip-based membership protocol. And failure detection, again, we're not going to cover a lot. We're focusing on the top three things. So this, as the name, you can just try to understand it by what the surface meaning. It's like the node will keep gossiping with its neighbors, what happens, the knowledge of the system. So that's how the knowledge of the whole system gets propagated to different nodes, like by node periodically gossiping with a few neighboring nodes. And everyone knows something, and eventually you start to know most of the things happening in the system. Okay, first let's see the partitioning algorithm. So partitioning or sharding, we've already seen actually quite a few. So there's usually a partition or sharding key, right? Or shard key, sorry. MongoDB should be called a shard key. So there could be system default, like in big table, you can't really choose what is the partitioning key. It's only use the row key to partition the data, right? And a range of row key always put together in the tablet. So this called system default, and there's a user specified. That's like in MongoDB. You can specify the sharding key. Doesn't have to be the underscore ID, the primary key. Could be anything else. But there are certain restrictions on the sharding key. But nonetheless, it allows users to choose a sharding key based on their understanding of the potential queries. And so once the sharding key or partition key is decided, and then there's an algorithm to decide which data goes to which partition, right? It could be range partition, like, again, big table use range partition. So like each tablet, it's supposed to store like a range of the row keys, right? And MongoDB also has the range partition one, right? Like each chunk is supposed to store a range of keys. And each shard consists of multiple chunks. That's the MongoDB one. Or we can use the hash partition. And again, MongoDB also support that. It's basically you hash the origin. Instead of the original raw key value range, you hash the key, you get another value. And then the trunk, it stores the range of hash value instead of the original key values. So what happens like when data grows? So when we, so usually, initially it's always everything is pretty fine, but things might get not very, it's a bit hard to handle like when data grows. How do you like move the data if there's a lot more data and then can't really fit? So what happens? So in big table way is, yeah, it happens locally. So each partition, like the tablet, it may grow independently, right? And then whoever managed the tablet knows the size of it and then can decide if it's too big, we need to split. So it's like if it starts, so it always like starts small and then we keep splitting. We start with a single tablet, and then if it's too big, we split into two. And then these two might be managed by different servers. And then the server will monitor the size. And when it find out, okay, one is growing a bit big, and then it will, like this grows big, and then it will split into two. And then this will eventually, after it's split, initially managed by the same server, but need to be reported to the master, right? Which will probably load balancing it to some other servers. So it doesn't. So the good thing, it doesn't really have global impact, right? So only managed locally, and the local server will do the split, and then the other server doesn't really know. And it doesn't need to be involved unless it's eventually asked to manage a partition. That's the only thing. The other server might get involved. Well, the problem of this is state might not be evenly distributed in each partition. So some may be like reaching the tipping, like the partitioning point. Others may be just partitioned and it's pretty small. So that's something natural, like a result you can't really do much. So let's see what's hash partition. Hash partition that's the one we've seen in the previous memcache. That's what we call hash partition. So first you hash the key to a value, and then you do a vote, and then this gives you like ID. So the ID tells you which the location of the data. So it's like this is the hash value, keys hash value, and then we do a modular function. If initially we only have two partition, and then we have to mode 2, right? And we mode 2, and we have two partition. We got ID 0 and 1, and then they're managed by some server. And then we mode 2. Mode 2, we got 0, 2 here, and 1, 3 here. Now if, so hash partition, the benefit of hash partition is usually can distribute data more evenly compared with the range one, but it does have problem of repartition. So if the hash value of key is kind of evenly distributed, and then each partition will usually get roughly the same number of keys. But the disadvantages does have a lot of data movement when repartition happens, because it have a global impact. So if we have if we add some more data and then 2 partitions is not enough, we need 3 partitions. So that means we have to change the mode function to, now we have partition ID 0, 1, and 2. And we have to mode 3 now. And when we mode 3, so basically all many of the value will change the location. So some will still, so 0, 3 is here now. So 3 is no longer in 1, in 0. And also here is 1, 4. Okay, 1 stays, 4 is the new one, that's all right. So now 2 becomes here, and that's the new one. So it's like half of the data actually, we originally only have 4 keys, and half of them actually change their partition. So that's a small example. So in a large system, you can imagine this kind of repartition will have very large impact on the system. It involves a lot of data movement. So we use this if the data size is relatively stable, and we don't need to keep like adding like number of partitions. So we don't need to do a lot of like repartition, and then that's okay. But if it's very dynamic, like your data will probably keep growing, and you always need to add partitions, and then this is definitely not a very good mechanism. Okay. So this is the simple hash partition. But still, if we want to keep the good feature of hash partition, like usually we expect it to distribute keys evenly in each partition. But we want to mitigate this data movement during repartition. Like if we anticipate the size of the database is pretty dynamic. It might grow, it might shrink. And so the number of buckets, if we use this, number of partitions will change pretty often. So we can still use a hash partition, but not the very simple one. We can use a different hash partition. That's what Dynamo uses. It's called consistent hashing. So it's still hash partition, but not using the simple like modular function to do it. And it doesn't really identify each partition as a number in this 0 to n minus 1. So that's actually the top one cause for such like a great amount of data movement during repartition. So we get rid of this mechanism. So we don't really identify partition as a number in 0 to n minus 1 if there are n partitions. So instead, now we utilize, so we need to know something beforehand. That thing is the output range of the hash function. So we do have something stable, which is like we know we're going to use this hash function. And for different hash functions, it will give you like a different output range. So we're going to utilize that. So we have a hash function that's pre-selected, and that's stable. We're not going to change the hash function. Because for this one, you keep changing the modular function. That's not very good. And so here, we rely on the hash function and being stable, and it has an output range. And so we treat the output range as like a fixed circular space or ring. So from 0 to some maximum number. And the largest hash value wrapped back to the smallest one, like a 0. And so each partition basically represents a range in the whole ring space instead of identified by 0 to n minus 1. So we can identify it as like from 0 to some number, and then this number to another number. So it's always like a range. And the range is always in this output range space because they are stable. So whatever we choose is always something in the ring space because the ring space is pretty stable. So identified by a position like value called a token. So it's like we have a ring and we put some token randomly around the ring, and each token represents like a range. And the hash of a data record's key will uniquely locate the range. So we hash a data record, and we get a hash value, and the hash value is always somewhere in a certain range, right? Because it's always within the output range. And then it will have a unique location, and this location will decide which server basically serves it. And also, in a distributed system, each node represents like one partition or a number of partitions if virtual node is used. And then they represent like a range. So if we need more partition, more nodes, we basically add more tokens there. And then when we need to move data, it's only the partition like right next, like a few neighboring partitions will be affected, like we need to move data around, but it doesn't really have a global impact. Okay, so how does this get implemented in Dynamo? So first, each node in the Dynamo, so Dynamo is a cluster, and the cluster consists of multiple nodes, and every node is the same as the other node, so there's no master. The cluster might start with some nodes, and then later on, new nodes can be joined, and each node needs to have a token, and the token is like a number. The number should be within the output range of the hash function. And the token basically represents the node's location or position in the ring. And that also implies the partition it's served. So each node is responsible for the region in the ring between itself and its predecessor node. So each node has a token, right? So it's responsible for the range between its predecessor's value and its own values. And the ring space, so they choose the MD5 hash function, and this hash function will have a value of in 100, basically stored in 128 bits. So that's 0 to 2 to the 127 minus 1. And so then the key of any data record, and again, regardless of the actual data type of the key, so we can always use the MD5 hash, and it always, so any key, it doesn't matter whether it's a string or a data or a number or a complex object, it will be converted into this a number in this range. And then this is used to basically determine, okay, the location of the data and which server is managing it. And we will see how it works. This is like an example. Suppose we only have 4 nodes, and the ring space is pretty small, so we can use smaller number. It's like from 0 to 99. And there are 4 nodes, and each node pick a token. This node pick token 0, this pick 25, that's pick 50, that's 75. But usually, the random choice, it doesn't give you this very evenly distributed token, but that's fine. And usually, like when a node joins, it just randomly pick a token from the space, and then it could be kind of close to some node and a bit far away to others. That's So that's how we decide the range. So this is the ring, and then that's like going this way. And this is this node, and its predecessor's token is 0, so the range is from 0 to 25. So the open, close, here I'm just using this is open, this is closed. So it's like equal to 25, but greater than 0, and less than or equal to 25. And this one is like 75 to 0, so it's like from 76 or 75, assuming it's all integer. 76 to 0, up to 99 and then 0. So that's the range from 75 to 1. So that's from 25 to 50. So it's always the previous one and itself. That's the range. So if we have a row key, which is someone's names, B. Anson, B. Sanderson, and if it's hashed to a number 31, so it's basically in this range. Right? It's somewhere here. So that means, okay, this node is responsible for storing this. And this is called coordinator of this node. This key is called coordinator, which means it needs to coordinate something. It's because there will be replications, and the data need to be replicated to the other node. And that's the one, the coordinator of this particular key. So it's not the coordinator of the whole system. It's just a coordinator of some keys. So all the node eventually will take the coordinator role of the keys located in its range. Okay, I think I'll give you a 10 minutes break. Then we'll continue with the virtual nodes, like slight variation to the basic one. Okay. Okay, everyone, can you come back to your seat? So we will continue with the lecture. So just now we discussed the very basic consistent hashing algorithm where each node is responsible for a range, but that kind of assumes that each node is having similar capacity. Well, that's not always true because there's no such requirement that within the cluster every node should be have the very similar capacity. And also another thing is that the positions they're randomly assigned, so you can't really guarantee balanced distribution of data on node. In particular, if there's not many nodes in it and we have such a huge range, so it's possible if we don't have many partitions, and then some node might get a pretty big range and others get a pretty small range. And usually the way to solve it is breaking it down into many smaller ones, right? So then this comes then Dynamo actually used virtual nodes concept. So basically, this will increase the number of partitions to make sure we get better distribution of data. So it's virtual node basically means multiple positions or partitions per node or multiple tokens. So each node may have multiple tokens, and then the number of tokens can be determined by the actual capacity of the node. So for instance, we might have something like this. So this is a relatively not very powerful node, and this could be a pretty powerful node that's medium-sized node. So we probably give these two nodes 2 tokens, but of course that's just a toy example. In real world, they might have a lot more. And then we give this node 1 token, and we give this node 3 tokens because it's bigger. It's the biggest node. So now we only have 4 nodes, but we have actually more partitions because this node is responsible for 2 partitions, and this is for 2 partitions. This is for 3 partitions. This is for 1 partition. And the way to determine the partitions range it's the same. Basically, we have all these tokens, and we have to sort them in order. And then in between each, there's a partition. And then between the largest and the smallest, there's a partition as well. So it's this one. So between 10 to 20, that's a partition. And this partition should be served by this node, which has the token 20. So the previous node is the one with the token 10, which is this one. It's 10 to 20. And then we know this should be, because it has 0 and 40, so we look at, okay, 0 is going here, and 40 is here. It's 30 to 40. So that's 30 to 40 and 80 to 0 is this node. And this adds 30, 50, 80. So basically, by checking this list, so 30 is responsible for 20, 30, and 50 is responsible for 40, 50, and 80 is this. So we have that, and then we have that for this. So if we have same key hash to 31, it's located in the range 30 to 40, which should go here. So basically it's the same thing. It's now the only difference is instead of using physical node, we are having virtual node, and each physical node can support 1 or many virtual nodes. So remember, actually, this memcached has quite similar design consideration. One instance can have, with a lot of available memories, can be allocated with more than 1 bucket, right? And another maybe with 1 bucket. So this is the virtual bucket. Okay. So the virtual node rings consist of more nodes, and then the physical ones. So the physical node may appear in different positions in the ring now. So we have something like this. So this is representing 2 nodes. So we can use subscript A and B to represent it. And this represents 3 nodes, and this represents 2 nodes, and this just represents 1 node. So in total, we have 7 virtual nodes. No, 8. So there's 1 as well. And then this is how we put. So this is like the first one, which is this, and it's followed by this, which is the physical node 4, but it's the virtual node of the first virtual node of this physical node. And then we just, this is N2, and then we followed by N3A, N1B, and 3B, and like this. So we can still form a ring. Now it's just inside the ring we have virtual nodes, and they're actually located in the physical node. So like this node appears in these 3 positions and in the ring, and this node appears in these 2 positions, and this in these 2 positions. So that's the partitioning. And so this kind of suggests, okay, what is the main node for a key? But then we have to replicate the data, right? So just one copy definitely is not enough. We need to replicate it. And so in a big table doesn't really care about replication, right? So the replication is actually done by the GFS. And the MongoDB, the replica set, it's predetermined. So here, it's like you have like a shard, and then consists of replica set. So it's like predetermined when you set up the cluster. Dynamo has a little bit more dynamic way to decide the replication. Okay. So again, for any system with replication, there's a replication factor, which is the number of replicas you want to keep, and usually it's 3. Can be a different number, and so it has a replication factor. It also has something called coordinator, which you already know, and preference list. So that's the number of nodes. That's a list of nodes. The first few does have the copy, and the rest are like candidate node when the first few are not available. So the general principle is if the key is located in this particular range, as specified by this node, and then it should be replicated in the following node, subsequent node. And depending on the replication factor, like if the factor is 3, so you need to replicate 2 times, so it need to appear in this node and this node. So that's how we determine where the replication goes. So we always need to have an idea of the ring. When we have the ring, then we have an order of the node, whether it's physical or a virtual node. And so we determine the coordinator, which is the node that manage the range where the hash of key is located in. And then the subsequent nodes, the few subsequent nodes, like if it's n-1 subsequent node, is the one that supposed to store the replica. And then then we want to kind of increase the list because we want to have this always writable one. So the list of the node that is responsible for storing a particular key, and sometimes temporarily. So these are the permanent storage. There is a temporary storage. That's called preference list. And it might include this one, depending on how long you want how big your preference list should be. It usually contains like more than n to accommodate for node failures. So like if a few of this is not available, and then this one can be considered as like a temporary storage for this key. So the preference list will contain its designated replica node plus a few extra nodes on the ring, subsequent node on the rings. So it's a list, but you don't really need to store it because it can be computed on the fly by any node in the system, as long as they know the other node's tokens. And then this knowledge is it's spread, propagated to every node through this gossip protocol. Like every node knows its own token, and it knows a few nodes in the system, so it will try to communicate with those nodes to exchange information. And then gradually it will know the token of all the nodes, like the existence of all the nodes, and then the token they manage. So they have this, each node will keep this knowledge, and will also keep updating this knowledge, like if a new node joins in or some node leaves. And again, that will be propagated to the system, and eventually every node will have this global knowledge. So the preference list of this node in this Choi example basically kind of consists everything. C is the coordinator, and then D and A are the designated like copies, and then B is the one responsible for the temporary storage. Okay, so let's see what happens when there's replication with virtual nodes. Because replication means we definitely we need to have a copy in different node. We don't want to store like 2 copies in the same node. That doesn't really make sense. But if following the simple principle, it might happen. Like we only go to the next few subsequent nodes, and it could be the same node, because remember, now a node can occur in multiple locations. The same physical node can occur in multiple locations in the ring. So in replication with a virtual node, we still want to ensure that the replica exists in different physical nodes. So we have to skip the duplicated physical node when we compute the preference list to make sure it consists of all unique physical nodes. So for instance, if a key has a coordinator here, and then it can be stored here, right? That's a different physical node, it's N1. The right next to it is N3 again, so we can't do it. We have to we're not going to store another copy, so we have to skip it. And then the next is N4, that's all right. So these two are the nodes that will store a designated copy of K. So basically N3, N1, and N4, they are the node that usually supposed to be like store a copy of this key all the time. But then remember, the preference list, we do need to include a few other nodes, and again need to be a different physical node. So we move along the ring. Okay, N3 is already in the list, so we have to skip. N1 already in the list, or we have to skip. N4 is in the list, so we have to skip. So eventually we put N2 in. So we have to skip quite a few. So the idea is it needs to be different physical node. And this still can be computed on the fly. Okay, yeah, I already mentioned that the membership and the failure detection, they are all spread out. The knowledge of the cluster is spread to all the nodes using something called gossip protocol. So when like a node is joining the cluster, and it picks one or a few tokens, and then it needs to know some node in the cluster. Otherwise, there's no way you can join, right? You have to know some node. And then joining means you pick some token, and then you tell the node that you already know in the cluster, this is, like I'm joining, this is my token. And those nodes basically also know some other node in the cluster, and then they will gossip with the other node. And then eventually this is spread to the whole system. And the failure detection is also through this gossip. And it's pretty local knowledge, and it's pretty temporary. So you might it's like periodically you try to exchange some information with your neighboring node, and if you can't really get a response, and you can flag this node is currently not available, and then you can spread this to your other neighbors. But this is basically temporary, so we don't need to have all nodes to agree. Okay, that node is not available, because the node might be just temporarily not available, or it could be just the network is having some issues, and maybe after a short period of time it just comes back. So that one is kind of okay. So some node will know a few other node is not available, and then when they try to direct the queries, they will avoid that node. But then after some time, it might receive information this node is back, and then they can flag this back. So that's just handle very temporarily node failure to basically avoid communication cost. Like if this is sent to the unavailable node. So that's not mean it's permanently dead. So the permanent node departure basically needs to be handled outside by administrator. Like node joining in or leave needs to be handled by administrator basically. When you pick a token or something, it's more like we have to start a process in a cluster, and then some administrator needs to do that. And this one as well, permanent node departure is we're going to maybe kill the process running on a node, which managing the dynamo. So the administrator needs to do it, and then before just brutally kill the processor, it needs to do some cleaning up things. So that's all handled externally, and then the data handled by node will be gradually transferred to the others. Not from this node, but from the other copies. So it's we want to add storage node. Again, here we use this toy example. We don't really care whether it's a physical or virtual. We just it's node. Currently having 4 nodes, and when we add a node here, pick a token 10. So basically means it's sitting here in this range. Now it's looking after the hash range between 0 to 10. So it's now this node changed its range from 0 to 25. Now it got smaller, 10 to 25 now. So that means looks like there are quite a few data movements in this toy example. But if you put the whole thing in a very large cluster, so it's still a local movement. So basically it means it needs to receive data in this range and serve as coordinator. So it receives from here, right? Initially, all the data in this range is kind of coordinated by this. So we can receive data. So this will need to send something there. And also need to receive data from in range 75 to 0 and serve as replica, because now it's the direct subsequent of this. So it's the one that should keep a copy of the data in this range. So we have to receive some data there. And it also, because it's the second in row for this one, so it needs to receive data in this range and serve as replica as well. So only a small amount of data change their coordinator node, which is this range changed, but quite a few range of data change their replicas. So this is no longer coordinator for this key, and also no longer replica for that range in this, because now it's the third in row now. And also, this is no longer a replica for data in range 0 to 10, because now 0 to 10 is here. So that's the first one, that's the second one. So this one shouldn't serve that. Okay, now let's see how read and write is handled in Dynamo with this replication scheme. Also, like in general. So we've already seen in MongoDB how this is implemented. And that's kind of, yeah, that's one way. And Dynamo using a very different way. So there are many options. So the typical one is, yeah, there's a typical one. Like write happens on the master and may propagate to the replica, right? Immediately and wait for all acts before declaring success. That's more like the MongoDB way. Or lazily and declare success after the master finished write. And the read may happen on the master, which if we want strong consistency, or at one replica, which may get stale data. That's a very typical way, and that's how MongoDB does things. And then MongoDB try to keep different snapshots of the data, right? So it can serve data with like quorum write or just like local update. So so that's the environment where there's a designated master or coordinator, and then it can handle all of this. So it can, but when environment where there's no such things, so we do need to use other mechanisms to ensure like certain level of consistency. This is like in Dynamo's case, where we don't really have a designated master or coordinator. So basically, we want to ensure like so all the replicas will see a consistent order of concurrent write. It's not like if there's concurrent write and then different replicas see it in a different way, and then they can't agree on the final value. And we also need to worry about like how many replicas to contact before answering or acknowledging. Like in MongoDB, usually read just contact one replica. It doesn't need to worry too much. But here, you may need to also worry about for read, like how many you want to contact to ensure certain consistency, because different replica might have different values. If you contact more, you get some idea of this is the latest and that is the old value, and you can pick the latest value to return to the users. Okay, let's see what does this mean. Assuming every replica can receive write, not like only a particular node receive write. So like different clients may try to update an item simultaneously, and they might contact different replicas because they're all the same. So like if one client contact this first and the other contact this first, because they are like this client is physically closer to this replica, and this client is physically closer to this replica. So they basically contact the closest one, and then this receive the write, and then try to propagate to the others, and propagate to the others. So if nothing is done, and basically the two replica is updating the same data in different order, right? So this is first write 8, then write 5, and this is, and for this replica it's write 5, and then write 8. So they end up with different value, one with final value 5, and the other with final value 8. So that's definitely not what we want. And then there's no consistency at all. So how do we do it? Usually we use something called timestamp to assuming we have a way to assign the time, and they're all in the order. So yeah, it's a typical way to order the concurrent writes. So instead of just send a write, we also attach a timestamp, like when the write happens. And assuming here, we kind of assume we have a global clock, like all the clients, and then like kind of synchronize the global clock. Yeah, so we associate the timestamp on the right, and the higher timestamp kind of wins. That is more recent. So if this has a timestamp 1 and this has a timestamp 2, right? And again, same thing. This client write to replica 1 first, and then propagate it to replica 2, and this write replica 2 first and propagate to replica 1. And goes here, that's okay because it has received a write with a TS1, and then we receive a write with TS2, and 2 is like later, so we can apply it, and the final value is 5. But when this arrives, now because this one already receives like a write with timestamp 2, which is supposed to subsume any previous write, and then when it receives a write with timestamp 1, like early 1, so it will ignore this change because it's like an early write, but it arrives late, so we don't need to apply it because the final value should be 5. That's as written by the next write, so it will be ignored. So this, of course, this is a very simplified example, assuming like all the clients has like a synchronized like time clock, and then all of these are in good orders. But you will see, like in distributed system, it's really hard to achieve that. So Dynamo use something, try to build certain orders. Okay, so that's one way, ordering. And the other way is when we have multiple copies, and then basically a write needs to reach some copies, and a read also needs to reach a few copies. Because usually we don't really assume that write needs to write on all copies before it returns to the client. That will be very, performance-wise, it's not desirable. So usually there is some number you decide, okay, like write needs to, MongoDB also has that for write concern, right? Write needs to reach maybe a few, maybe at least 2 replicas before telling the client success. So it's same here. We can have a number saying like how many replicas need to be updated before telling the client the write is successful. And then how do we find the current value of the item when reading? Like if we always want to find the current value, and assuming that write will return without reaching all the copies. And then we need to ask a few, when we do read, we also need to contact a few copies, right? And the idea is if we contact enough copy, and then some will contain the latest one, and then we can return the latest one. If we only contact 1 copy, and we might be unlucky to just contact the one that hasn't been updated yet. But if we contact enough copy, and then the chance of getting one that is having the latest value is, if it's guaranteed, and then we can always return the latest value. So that's what we call the quorum approach. So it's look at like R replicas, and of course there should be some features of W and R to make sure that there's always the replica that has been updated, has the latest value, is always contacted. So basically this is, so we need to write to happens on n more than half of that's majority of the node, and also read plus write should be greater than the n, which is the replication factor. So in that case, there will be a common copy between read and write, right? Because if R plus W is greater than n, that means at least there's 1 copy that is common, called intersects. And then that one will have the latest value, and then you can always return the current values. Okay, so let's see how this is implemented in Dynamo. So one is, how do we implement the timestamp? So that's called the vector clock. So it's a way to implement the timestamp concept in distributed system. It's not a single value, because usually it's pretty hard to synchronize all the clocks. And also, it's aid for resolving version conflict. So the idea, it has been proposed a long time ago, and Dynamo is just proposed a way to implement it. So that has been a classic question in distributed system, how to kind of sort the event in order. Yeah, it's basically like when the read receives R copies, how do we decide, like, this one's the latest. There's like a causal order among all the copies. And then if there is, what is the latest? And if there is not, what do we do? So vector clock kind of is used to help solving that. It's like a timestamp, but not a single value. And then, so if we're using this quorum mechanism, so which means, and we have this W and R, so that's kind of say we always need to contact this amount of servers. And then, and in classical way, so the servers you can contact is kind of it's kind of predefined, right? You should only contact those servers that has a copy, supposed to have a copy of the data. But there's possibility like maybe more than half of the server that actually has a copy is done at the same time. And then in the classical way, you can't really, your write can't be successful because you need more than half of it. So, but Dynamo wants to have this always writable feature. So they use something, they slightly modify the quorum mechanism, use something called slopy quorum plus hinted handoff. Basically, they include server that is not part of that is not permanently, have a permanent storage of the data to be part of the quorum, to join the write, so that we can always have some copies somewhere and then tell the client your write is successful. Okay, let's see what's the read and write route. First, again, when a client needs to communicate with the cluster, it doesn't need to know a particular node. As long as the client knows some node in the cluster, it doesn't need to know like every node or which data is in which node. So as long as the client knows some node in the cluster, it can send a query to that node. So any node is eligible to receive the client read and write request. It probably doesn't really answer it, but it will direct the request to the node that can answer it, but it can receive it. So the read and write request is only a very simple one, get key or put key and value in. So it only supports these two simple things. And yeah, the node receives will direct to the node that has the data and is available. And usually it's the coordinator node. It's like the first one in the preference list. So it's able to do that because any node knows the token of other nodes through gossip. And it can compute the hash of the key in the request. So any node can compute the hash because it uses the same hash function. And it can compute the preference nodes. And it also has local knowledge of node failure. So it kind of knows, okay, I should send to this or that node. So the node handling read or write operation is known as the coordinator. So any read or write coordination will have some coordinator. And most likely the coordinator is the coordinator of the key. It's the first one in the preference list, which is the one that is supposed to store the range of that key. Right? Only when that one is not available and another node on the list of the subsequent node on the preference list can work as the coordinator. But most of the time it's that same node working as the coordinator of the same key. So every node is like the coordinator of some operation. For the key, it's responsible. And for a given key, it's usually handled by the same node, unless it's not available. Okay, so what's the data version here? So typically there's a write call. This is the write, put is a write, and the get is read. And we have this, we use the quorum mechanism. We have this W, we have this R value, and usually the n is 3 replication factor, and we have W equals 2 and R equals 2. So we satisfy this feature that W needs to be greater than half of n, and W plus R is greater than n. So this will ensure we always get the latest version. But the challenging here, but still, because we use slopy quorum, so sometimes we don't. yeah, how do we manage the version now? So use the vector clock, like the timestamp. So it's used to capture the causality between different versions of the same object. Yeah, because W is less than N, so then it will end up with like some replica has the more recent one and others may have the old ones. And so they're different versions. The causality means if the version is directly in front of, before the other version, is like when the writer is actually updating that version. Okay, so what is vector clock? It's a list of node and counter pairs. And one vector clock is associated with like every version of every object, the current version of the current object. So it's like every replica of the object has like a vector clock. And it could be the same or could be different. So how do we interpret this? This is like example. So this is a node. Node has identification. And then there's a counter, which is just a number. And each node has its unique identification. So this is a vector clock. And that's another vector clock. This is a list. Right? Each list has some element, and each element of the list is a pair of node and counters. So node refers to the node that coordinates the right. And counter remembers how many times this node has coordinated the right of this particular key. So what does this one mean? So it means this version of the object has been updated twice, because see, we have like there's one, so that one is coordinated by N0 and the other is like coordinated by N1. So usually because we put N0 as the first one, so it's like this is the initial insert. So initially this needs to be inserted. The first write is always like a put. And this like handled by N0. And then next time when we want to update it, N0 is not available, so N1 did coordinate the right, so we add an entry for N1 here, and N1 did it once. And what does this mean? Okay, this means like the version has been updated 5 times, because how many times you can just look at this. So it's like twice here, and once here, and twice here, so like 5 times. And this is the first one, so it's M1 is like coordinate the initial insert, like the put. And then after that, it's being updated 4 times. But then we don't really know. So this can't really tell you, okay, whether the second is being done by N1 as well, or the second is being done by N2 or by N3. This you can't tell, and it's not that important. So the other order, we can't establish the whole history, but that's not required, because it's not really designed for remembering the entire coordination history. It's mainly for, like, when we look at 2 of them, we can tell this one is before that one, or these 2 are kind of parallel. So it's always looked at in pairs. So we don't really look at one. That doesn't really make much sense. It's always we have like 2 vector clocks, and then we want to see, okay, which one is like in front of the other one, which one is early, which one is later, is more latest. Okay, so how do we decide the causal ordering? By looking at like a pair of vector clocks. So there are 2 like possible, when you look at 2 vector clocks and they belong to the same object, and there are only like 2 conclusions you can get. One is, okay, there's a causal ordering. One is in front of the other, and the other is we can't build up ordering. So they are in parallel branch. Like they somehow get updated separately, and we don't know which one should be is the first. Okay, so how do we know? So like if the counter on the first object's clock is less than or equal to all of the nodes in the second clock. I know it's a bit hard to understand. That's from the original paper, but we'll use the example to explain it. Then the first one is like ancestor of the second and can be ignored. Otherwise, they're considered to be like in parallel branch. So let's see example of these two. These two, if we have two versions, and one version has, of the same data, one version has this vector clock, one version has this vector clock, and we can tell this version is after this. So this is the ancestor, because look, so this has n0 and this has n0. So this n0's counter is smaller than this n0's counter, right? And this has n1, and this also has n1, and it's equal. And this has n3, this doesn't have, that's okay. So we kind of know, because this has 2 update, and this one is like, so it's not actually 3 update ahead. So this is like 4 updates, and this is 2 updates. So it's like 2 updates ahead of the first one. So they were, there's no branch actually. So it's just after this, and then N1 and 0 made another update, and N3 made another update, but somehow this one is not really updated, but it's derived from here. So these two, we can't establish the causal relationship, because we can't say this is before this or this is before that, because okay, from N0 it looks like, because the counter of N0 here is 1 and counter of N0 here is 2, it looks like this one is in front of that. But then this one has N1, which doesn't appear here, and this has N2. So it's like, we can't say it's less than or equal to all of the nodes here, because this one actually has a node. This one is missing N1. So they are like in parallel branch. And we can know that what's their common ancestor. So the common ancestor basically is this N01, right? So after this, they branch off. So this version is get updated by N1 once, and this version is get updated by N0 once, and also get updated by N2 once. So they happen in parallel time. So this is what we call the branching off. And we don't know which happened first. So they are in parallel version. And once we get this two, if we get this two during a write, that's all right. We don't need to worry, because we are going to have a latest write and then can subsume all the previous ones. That's all right. But if we get a read, and then we can't really get it from a read, and we can't really decide, so we might have to return this to the client. And the client can pick whichever one they want. Okay, so how do we update with vector clock? So remember, each replica stores a copy of an object, and the object should be associated with like a vector clock, and that's indicated the version. And each machine might have slightly different vector clock, because they might be unavailable during some write and will miss maybe one or few writes, and then they get picked up and then continue with the others. And then at the same time, some other machine might be down. So it's possible the different replicas may have different versions and indicated by different vector clock. So both read and write will need to contact multiple replicas and obtain multiple versions, and they need to decide, and they need to compare it and then decide what to do. So how do we do update? So during update, when a client needs to update an object, it always needs to indicate which version I'm going to update. And how does the client know the version it needs to update? So it's done by doing a read. It could be previous, like a read it needs to do, or if it hasn't done any read, it needs to read first and then do the write. So the context basically, like the context is what version I'm going to update. It should be obtained from an early read option, and which contains the vector clock option information. So when we process a read request, and if Dynamo access multiple branches that cannot be resolved, like we cannot establish the order, and it will return all of them with the corresponding versions. And so this can be written directly to the client for the client to resolve, and then during write, this can be sent to the write together with the write, and then the write will duly recording all of them, and to make sure so the latest write is from all the previous branches. So it's like now we're merging them together. Now let's see an example of this one. So there's an initial insert requested by C1, coordinated by SX. So we got a version D1, and it has the vector clock SX1, and then 1, right? It update once. And then C1, the same one, wants to update D1. And this is coordinated by SX again. So we know this. We're updating this, and then we just increment the counter because SX does the coordination second time. And now, if C1 wants to update this version, and now it's coordinated by SY because SX somehow is not available. So it's updating this version and it's coordinated by SX, SY. So create D3, and by adding an entry for SY now, because it's not coordinated by SY. Now, suppose C2 reads the object. There's a C2. And when it's read, it needs to contact multiple copies. If it gets both D1 and D2, if D1 is somehow lingering in the system, some copy still has D1. So if C2 receives D1 and D2, it actually knows, we can easily know D2 is earlier than D1, and D1 can be garbage collected. So it can actually tell the replica holding it that D2 is the most recent one. So we'll return D2. And now it already has D2. It wants to update D2, and somehow it's both X and Y probably is not available. So it gets handled by SZ. And so this SZ is not aware of D3. It's only aware of D2. So when it do the update, it creates D4, and by adding its own entry as Z1. Now these are what we call a parallel branch. These two has no, they both descend from S2, but they're not really related with each other. Now, if there is a C3 and wants to update object, then you need to do a read. And when it does a read, it may receive both of these. And it can't really decide on what to do because they're in parallel. So both will be included in the context when sent to the write. So it said, okay, I'm going to update these two copies. And then suppose this is handled by SX. And so it needs to include all previous in the vector clock because it's descendant from both. It can't say I'm only descendant from this or descendant from this. So it needs to put all of this in. So SY is here, SZ1 is here as well. But because it's handled by SX, so we update the SX counter by 1. So we get SX3 and then all of this. So now anyone receive this 2 will know, okay, D5 is the latest. Anyone receive this 2 will know D5 is the latest. So this is like now we're branching off and we're merging back. So that's the reason why we need to send all conflicting version and eventually get merged back. Yeah, so the size of the vector clock is relatively small. The size was the list because only the nodes that coordinate the write will have an entry in the vector clock, right? And usually, like if the preference list contains only 4 nodes, and then the majority of the vector clocks will contain up to 4 entries, right? But in rare situation, when all nodes in the preference list is not available, and then Dynamo will find some other node, and then will add another entry. And if this happens quite often to some key, and then that key will probably have a pretty long vector clock. So it does have a truncate mechanism to remove the oldest entry, which you think it might no longer be used. We need additional timestamp here to determine what is the oldest entry, because here you don't really know whether SZ's oldest or SY's oldest, so they add some timestamp there. But this is pretty heuristic and very simple, so it might really remove histories that are needed in reconciliation, but it's something they still explore, and because it's never really occurred in real life, so it's not really explored extensively. So that's like following the design principle. We don't really design for everything. We sometimes just, because for the rare occasion, we only try to solve it when we actually has the problem. Okay, let's see a few more examples. So in a system with like 6 nodes, N0 to N5, for a key with preference list like N1 to N4, what has causal order? If we have something like this, if this is a pair, can we decide which one is earlier for this one? If one version has a vector clock like this, another version has a vector clock like this, can we safely say one is early, the other is late, and the early one can be garbage collected? Yeah. Yeah, this is the ancestor of the first one, right? Because it's, yeah, this is included here. And so this has 2 updates made by N2 after the first one. So what about this? This one you can't, right? Because there's N3 and this one has N2, so they don't even have, so none of them have a subset of the other, of the node. So we know they branch off. And they very likely branch off at some, like this with M1, 2. That's the common ancestor. And what about this? Yeah, so this is earlier than this, right? So we know this is like this because they, like N1, 2 is smaller than 4, and N3 is the same, and this one has extra. So this one is a bit more like recent than this. It has actually goes through a few updates since this one. And again, we don't really know the order of the update, but we know it's like a few updates ahead of this one. Okay, so yeah, briefly, what is slow p-quorum? That's basically a very simple mechanism. We just try to include quorum members that doesn't store a replica, and the purpose is to make sure high availability and write always happens. So first, we make sure the preference list is larger than n,